before record. So if you have seen in our last classes, we already know how to design a part and how to partition them and how to assign a CFRP materials to that particular soil, all those things that we have already seen. So again, today also, I'm just going to do the same thing for you. And you have said like a carbon fiber with the multiple things that you are going to get, but in that particular cases, CFRP, I just want
Sir,
to, yes.
the more I would like to learn about, sir, how to model a damaged column, sir, such a column which has loosened its stiffness, a column, kind of a column which has earlier stuck by an earthquake, sir.
Yeah, I'll tell you that also. That's not an
Yes,
issue. Losing its stiffness is nothing, but you have to, any cross-sectional damage it is happening.
no, sir, just minor, there are cracks in the column. So,
Okay. We can't do this crack generation and all because for a crack
yes, sir.
again, you should be knowing about XFEM and all, and those knowing all those particular details will be like more difficult and challenge now. So I don't
Yes, sir.
recommend to get into that particular part of a fatigue life. So
Yes, sir.
I'll just try to explain you about this itself. It's very simple. See, coming on to your question, like how to go up with the damaged things and all. When you're just going for a properties and when you're trying to define this material properties, every time that you are defining your elasticity, right? Elastic modulus, you are defining it, Young's modulus and Poisson's ratio.
Poison's ratio.
Okay, so as the time goes on, like let's say some 2 years or 10 years or 20 years, so the stiffness of this particular beam has been drastically come down. So you have to change this particular value. What is the reduction value you have to identify, and you just feed that particular value so that you can see the difference in the results.
Okay, sir. Okay, sir.
Okay. So again, I
Yes, sir.
said, so try in this particular way. It is just as simple as like reducing the stiffness of this particular column and all. It's like,
Okay, sir.
is there anything going to be any kind of mass loss or something? It's going to be
No, sir, no mass loss.
okay. And remember one more thing also, as actually when you are just trying to drop down the Young's modulus, it's not as simple as like simply reducing the Young's modulus, because when you are just going up to present this particular things, people may ask you a particular questions, especially on what basis that you have reduced it. So you should be having a proper validation with your paper, you should be showing some paper. If you are
Yes,
not
sir.
showing any kind of a paper or something, then once again, oh, there's one technical question they will ask you on this. I would like to present you this particular technical questions over here. Let's say I have something like this. This is my Young's modulus was stress versus strain curve actually. When I
Yes,
just
sir.
go with like a stress versus strain curve, and I'm just going to my Young's modulus as like this. So from here, I'm just going to cut this, and I will say this is my yield stress. And from here, I can say this is something around like a 0.2% of a strain or something by default for the metals. Okay, so this angle is like a 45 degrees an angle that's going on. And whenever I just try to plot a slope in this, whenever I just try to plot a slope value in this is like stress versus strain. When I'm trying to plot this particular slope value until this particular yield point, my Young's modulus is going to be same. When you are going for a material for degradation, when you are trying to change this particular Young's modulus, that means indirectly you are controlling your yield point also. So now your yield point will also come down. Yield point will also come down. So you should be identifying that initially when you are just trying to model your damage for the, sorry, that's plasticity concrete damage plasticity that when you are going it. So you should be identifying all the values. You should be identifying all the values like at the degradation level, what's the dilatancy angle, eccentricity and viscosity parameters, what is a compressive yield stress behavior at the damaged failure criteria. So you have to identify all these particular factors. It's as simple like when you just change this particular Young's modulus, it's meaning that this particular line you are just trying to modifying like this. And in that particular cases, maybe like your Young's modulus may come down, like sorry, yield stress may come down. So this particular point may be also like an yield strain may also little change over here. Okay, it will happen it like this. So these are all the things that you have to make sure in your reminder. And if you could not able to justify all the values with your limited resources available, if you could not able to justify all these particular things, but make sure that in a paper, make a present or like keep it in your mind and say when an interviewer or like when an reviewer is asking a question stating that if you are changing an Young's modulus, will this affect all the other values? Yes, absolutely. It's going to be affect all the values. Absolutely, it's going to affect all the values. But with my limited resources, it's very hard for me to identify all those particular values. So that's why I would be considering that my elastic modulus reduction value only I'm considering it. Then how you are justifying your results based upon these particular values and all. Then you can say that, let's say initially, I have my elastic modulus as like 25 to 50 000 MPa. I have like this. Now the new elastic modulus is that you are just mentioning it as like 200 MPa. When you just go about these particular two values, the new value is like 200 and the old value is nothing but 250. When you just go with this, what it is happening, the difference between these two is 20%. The difference between these two is 20%. So there is a 20% reduction. So all the way by considering that as a linear approximations, you can able to reduce all the values by 20%. You can able to reduce all the values by 20%. This is the best correlation I can do. Then they can ask you one more question like, when you just go for damage for ductile materials of a Johnson, plasticity, concrete damage plasticity, that when you are going at, this is completely a non-linear curve, right? Then how can you make an assumptions of a linear things and all? Anyways, I don't have any other option to identify those particular values. I have only a one option left over here is like the Young's modulus. So from the Young's modulus, I clearly understood that my yield stress is going to be changed. So when I reduce my Young's modulus by 20%, I'm going to reduce my yield stress also by 20% and yield strain is also by another 20%. So that completely I'm just scaling down my particular model as an assumption. That's what an assumption I'm doing it and I'm running for the solutions. This is an experimental trial that I'm going it. Maybe you should write another statement that when you go for realistic conditions, this may be the trend may be of a linear fashion or the trend may be of a non-linear fashion. So you might have studied some kind of papers in this particular way, saying that when the concrete blocks are damaged over a while, then what is the degradation material properties also you should identify that. If you could able to identify those particular properties, then it's really appreciable thing. If it is not, then this is the way that you have to go and minimize all these particular values and then feed it and give. These are the technical statements that you give. I'm not telling that this is going to be the 100% perfect way, but this is one of the best practices that normally we do in our industries.
Okay, sir.
When there is a
Yes.
no material properties is available, this is just an assumption only. I'm not saying that the results are going to be 100% correct, but instead of not doing nothing, we know like when you change an elastic modulus, there are factors that's going to be influenced by the other parameters also. So we should be remember all those particular parameters in your mind, and then we have to play along with that.
Okay, sir.
You got me what I'm saying?
Yes, sir. Yes, sir.
Okay, so you should do that. So your first next step is when you are talking about the damaged material properties, similar to that. In Dennis project, actually, he was saying that like, I have a bridge initially a mass having this much, and there is a material loss they were saying for over a period of some 5 years. The complete mass of a bridge has been reduced by something 20%. And because of that, what is the change in the density they have? Change in density they have, but material damage is not there. But here for you, mass is constant, but there is a material weakness is happening. So material, it's losing its stiffness. Now try to
Yes, sir.
understand the reason of why it will lose the stiffness. Why it will lose the stiffness over a year?
Sir?
Why over a period of a time, why actually your concrete will lose the stiffness?
One of the reason is that it has been stuck by an earthquake.
So that means what's happening internally?
Internally, cracks have been developed, and also um, I guess only cracks.
It's a cracks, and again, it's a reaching from an elastic region to a plastic region also.
Yes,
It may enter from an elasticity conditions to your plastic conditions.
plastic.
But
Yes,
in civil industries, no of our designs will never touch to a plastic conditions. We always try to stand at elastic conditions only, because a little
plastic.
deformation is also not allowed for us.
Yes, sir.
Okay, so we always stand for this thing. That's the statement that you have to give when the people are saying that in our industries we always stick on to a linear elastic things only. That's why I have made an assumptions with an Hooke's law. I have made an assumptions with the Hooke's law, and then I'm trying to degrade my model in this particular fashion.
Okay.
Okay, again, as to my particular statements, you have to figure out any particular papers are available. If papers are available, then no one will question you, right?
Yes, sir.
Okay, so try to see like people might have done a comparison between a degradable, like a decomposed, or like some over in years how concrete beams are degrading.
Yes, sir.
Okay, so I have seen one particular paper regarding for you, like day before yesterday when I was not well, that I was just going about this. Something is this, because I was reading in a mobile and kinds of causes of concrete distortion. Yeah. This is where simple, any material we are just going to feed in this particular way. So and then yeah, just before getting into that, let me finish this also. So when you are just going for like CFRP or carbon fiber, so let's say that when I'm just going with the carbon fiber material properties, that you have to go and you have to feed your density values over here. So density values, you know that we are feeding in terms of like turns only, right? So the density is 1.78 to the power of -9 turns per mm cube. Then going for elasticity, go to elastic over here. This is not an isotropic material. So this we are going with like a lamina. So you can just choose a lamina over here. And over the lamina that you can start feeding these particular Young's modulus values and all that. Maybe the Young's modulus over here is like in terms of like an MPa, I'm just feeding it. Maybe here I can say like it's a similar thing in all the directions. So I can just go all this particular one. Yes, and then I can just go here for sub options and you can go, it's a fail strain model. Anu, 1 second, Ashish.
Yes, sir, yes, sir.
Yeah, I'm sorry. So I'm just going here like a Z1, all these particular values, the Poisson's ratio in that particular plane and shear ratios in all the different planes that you need to feed. And then you have to go your sub options fail strain model. So in the fail strain model that you have to feed these particular values. That's any temperature dependent values. If you know, then you can switch on this use temperature dependent values. Otherwise, you can go with like a tensile stress in fiber directions. So normally tensile stress in fiber directions would be around a bigger value only. But a compressive stress in fiber directions is like a very smaller values. And transverse also I can just go with a similar because both the Young's modulus are same, right? So this will also come similar. This is 0 and cross product term coefficient. Normally identifying or getting these particular values is quite challenging one. So I always make it a 0 because we won't get these things and all. And stress limit also, we can just mention the same value. So just give okay. These are the parameters that we need to define your carbon fiber. So these are the parameters that you need to define your carbon fiber. Similarly, carbon fiber is not required for you because you are working on a degradation concrete beam. Surrounded to that, you are wrapping this. So no need of degradation of composite fiber is also required it or it's not required, right?
No, sir, no, sir.
Yeah, so you can just stick on to these particular values and just give okay. And later on, you just go like, let me build one particular small extrusion part itself. There are plenty of methods to go, though the method I'm telling you is around about the method, but it's quite comfortable to remember it. The other methods you will get confused and assigning all those things. Let's say this is the one that I'm just going here. Okay, let's say this is a small piece that I'm just going with that. Then you can go to your properties. You can go assign solid homogeneous, so carbon fiber. Then you can go assign a section. You can select this complete things and give up that particular material. You're just simply feeding these particular materials and all. Okay, so while calculating this, I think sometime back I have given you the failure criteria of a carbon fiber for a composite material. So that particular PDF I have shared you, right?
Yes, sir, yes, sir, you shared it.
Okay, so you have to go to that particular PDF file for a carbon fiber. What is the failure criteria you see, and then you can plot those particular respective stresses, calculate the put those particular stresses in that particular formulae and try to get the values and see whether your stress is safe or it is not. Like that, you have to validate your carbon fiber.
Yes, sir.
Got me?
Yes, sir. Yes, sir.
Okay, so simply you can just able to simply assign this particular things and all. There are plenty of things. Not this one. Cast place and concrete minimum cover. That's not this one, I think. Would not able to save the paper and so. This is with soil water exposure. Damage evaluation of why it got hanged up. This is complete process they're trying to do this. I'm sorry. Okay, if I figure out that particular paper, then I will share you out. Not this one. They have similarly talking about this kind of behavior actually. As what I mentioned here. So in the same way, they were just talking about this. So let me figure out in some time and then I can give you maybe in mobile history, if it is available, then I can share you those particular things.
Sure,
Okay.
sir. Sure.
This carbon fiber you can draw, and in this in between that, then you have to go your concrete block and you can able to assign this, and between these two that you can able to join this thing. Okay, let me go on this. Go to my part that whenever you want, you have asked me like how to edit this particular sketches. So I'm just going editing this particular sketch. So in editing this particular sketches, then we can just mention this height. Okay, let it be 25. Less will be 45. This would be 15. This will be 35. 15 by 35 I want. The side is 5. This side is 5. So when you do a over constraint, like you are giving a more number of dimensions and all, then it will shows you in a pink color. So in that particular case, you can just delete those dimensions. So this is 5, and what is this distance? This is also 5. This is also 5. So all the sides like 5 by 5, 5 by 5, I'm just going it. So that's done. 15 by 35, right? So feature. It's a feature regenerative. Yeah. But I'm just trying to go for another part. So I can just simply copy this particular part. Now I can say like concrete beam. Let's say I have something like concrete. That's the name. I'm just feeding it. Now to the concrete, I can go to the features. I can double click on this particular sketches. You can start. (15) and 35 we can leave. So we can start removing this. So I'm not going to disturb anything. I can just as it is like this and then. Okay, now I'm just going for feature and regenerate. Then this is how it's going to come. Okay, so this is simple. Now what I can do, I can just go to my assembly module and I can just able to bring my concrete and as well as this at the same time. So this will come as an insertion to this. Now this is one method. What I have discussed earlier is a different method. So in that method, what I'm trying to do, I'm just partitioning this and then I'm extruding this one. So the advantages and disadvantages of this method and that method is like, if you go partition and do that particular things, there is a no need to check for assembly constraints if it is coming correct or not. Okay. And the other parameter is like, you give any kind of a thing like you no need to check I need to give any kind of a tie constraints or something. Well, the method that initially what I have told with the partition things and all. But when you
Yes.
go with this particular method, then you have to give a tie connection between these two things, tie connection between these two. Like you have to
Okay,
go
sir.
to your interaction module. In the interaction module that you have to go for a tie constraints, and then you have to go continue this. So before continuing this tie constraints, let me take up images. So I can just go over here. These are the cells. So I can just remove this one. I can remove that particular cell. Go to tools, surface, create. I can just create a surface as a CFRP inner surface, continue, and I could able to select this. You have to hold shift over here, guys. Hope you remember that to multiple select it. I'm just holding the shift. Just give done. Okay. Then you can click on this invert display so that the other part is going to come. Now go to surfaces again, tools, surfaces, create. Now this is surface 2, right? So now it is concrete outer. I can say it's a concrete outer. Then you can choose this. Okay, you can choose this. You can choose this one. Just give okay. Now you can add both the things. This is a display group. So we have already discussed about this display groups also, right?
Yes, sir, we have.
Yeah. So now I'm just going here to the interactions and go here for a tie connection. So just go continue. You choose the surfaces. So here it's going to show the surfaces. Now concrete outer surface is my master because that is the most deformed material, right? So to the CFRP inner surfaces, that's a weaker material is my slave. So I can just continue. I can just click on this. Now a tie connections will happen on this. But when you just go like partition and extruding those particular things and all, even that particular tie connection is also not required. So straight away you can go for the analysis.
Okay.
But maybe in your case for CFRP, you can go with the partition wise. That's not a big problem.
So
But when
this
you
is
are
a
going,
much convenient way. This one,
the present one is a much convenient one.
sir. Hello.
Yeah, as your wish. Whatever you feel it's good, you can go with that.
Yes, sir.
Because the procedures are like a perspective point of view, right?
Yes, sir.
So whatever you feel is good, you can go. What the known procedures to me, I'm just telling you those things. So you can just go as simple as that. Now you can see this a tie connection. It has been built. Now you can see that particular tie connections. Okay. Now you can see that particular tie connections. It has been built completely. So that you can start applying some load over here, or like you can fix all these particular things and you can apply a load. You can fix the bottom, you can apply some pressure on this particular bar, everything that you can able to do it over here. I'm just showing you here is this. This is where like you can just go to a simple steps that you can create as an initial step. You can tell to Umnesh that if he is coming or not tomorrow, I'm going to tell the dynamics part because it's all stacking up your part also, right? You have to do earthquake analysis also, right?
Yes, sir.
Okay, so I'll start teaching that. Like you can inform to Dennis also, ask him to come. I'll put it in the group.
So what will be the tomorrow's timing, sir?
I will just confirm you by end of the day.
Okay, sir.
I'm sorry, these days, like it's a held up with many meetings.
So
So it's a fix that I'm doing it. So I can just able to fix. I'm just completely fixing up at the bottom. And then if you want, like you can just go apply some pressure at the top. So it's complete pressure. I'm just applying on it. Let's say it's a total force of something around 500 newtons. First, try to apply with a small that value, and then later on we can increase this particular value. Next, you have to go to the properties over here, and you have to assign a material properties for the concrete also. So as I don't know all the material properties of the concrete, just for a time being, I will just choose this particular material. As a stainless steel, I'm just choosing it. Okay, so you can just go assign the sections, choose that, and you can click on this. After that, you can just go to the mesh. You can go like part by part mesh and all. Now, people goes with another way, like here they can able to maintain the mesh connectivity between these two, and then they can able to achieve it. Even in that particular cases also, we may not require any kind of things, but this is not a software that's due for a very good mesh, but this is a mesh that we can able to create it. Okay, so after
yes, sir.
creating the mesh, you can just go to your job and then try to go for this one. Let me go put, you know, all the concrete material properties, how to feed, right?
Yes, sir. Material properties you taught, sir.
Yeah, so I'm just going here. So I'm just saving this model. So I'm going with 4 cores to my machine, so I can just submit. Now see this, there are some of the errors actually. Lamina can be used only with the plain stress elements actually. So, okay. So you could not able to use this particular methods. That's where they were saying that. So no problem. We just go for CFRP itself. They were saying that in the CFRP, yes, that's true actually. The Lamina model can be used only for a plain stress models. That means you have to model that as a 2D element, but that is not a requirement because we are going to partition sometimes, and then we were just going to do that particular part, right? So let me go and try in another way. Like this is a density, it's 1.78 e to the power of -9. Then just go with some mechanical, elastic, engineering constants. You can just go as an engineering constants. So in the engineering constants, that what I know is like I can go to the sub options, fail stress values I can feed, and then I can just go to or feed all my E1, E2, E3 values, all the E1 values, everything I can able to feed. So as I said, like some 225,000, we can go. It's 225,000. And the Young's modulus in third direction also it required it. So 225,000. And then the Poisson's ratio and the shear modulus I wanted. So I'm just going with all the values are same. Now I can just go to file stress model. Now this is all similar, like your transverse failure, compression side, and then transverse side, and compression side. Cross values, that's difficult, and the limit is 3,100. Same values only we were just going with. We are just going with an engineering constraint. So just give okay. Now material 3, you can just remember that it's a material 3. Yeah, this is where we can edit it. It's material 3 we can choose. That's it. This is how actually, when you just got an error also, you can right click on monitor over here and it will shows you those particular error messages and all. Elastic type lamina can be used with the plain stress elements only. How many number of an elements are there? Those many number of an error messages, it's going to show that. Okay. Now I have just changed it, right? So now try to submit this. Even this is got aborted. Why? Because anisotropic material properties without a local orientation system has been defined for 480 elements. Anisotropic materials properties must be defined a local orientation systems, and the systems had identified an element set. Okay. Now I know all these particular errors also before. I'm just trying to show you this particular things, how to read those particular errors, and then you can able to identify those things and all. I'm just going for results when that is throwing up an error. So let me go up this particular create a display group over here, and this is going to show like where the error elements are there. So now click on this, highlight this particular region. And then if you would like to replace this particular things, you can just replace this. So when I just replace this particular things, now it's clearly stating that again, my carbon fiber material property, it is showing an error. So it's saying that the local orientation, it is not there for this particular material property. So now when I just go over here, This is where, like, when I'm just trying to go for an engineering like when I'm just trying to go for mechanical elastic, and instead of an isotropic, when I'm just going an engineering constant, it's going to ask me all this particular values, right? So, or else the other procedure is like a laminar. So now I just need to give some kind of a local orientations for these kind of a materials and all. So to do that particular things, that what I can do, it's a local orientations. Okay, assign this material orientations because it's a carbon fiber. I'm telling that, but it should be lying up like in which directions that I just need to define this one. So I can just click on this and assign a material orientation. Select the regions that I would like to apply for this. Just go done and use the default orientations or the other methods. So use the default orientation methods. So whatever it is there, the global orientations method and the same orientation method that I'm just trying to fit it up. So just give OK. Now try to submit this. Now see this one, after giving up this particular orientations completed successfully. Now all the basic inputs it has been successfully given it. And then it is proceeding up for the calculations. Okay, now what's the errors actually here? This is how the other PDF that what I have given you, right? So this particular PDF will be start helping you for this one. So when I just look into this, initially my problem went well till certain time, but after that I have seen some couple of errors over here. That's what I want to discuss with you guys. Yeah, now see this one. It's all went like till the problem is going fine up to like 70% of my load. But after this, I can see there is some kind of a challenges over there. After this, some kind of a challenges over there. So this states that, let me go and observe the results first. Because a couple of steps has been generated perfectly. So now when I just go over here, go to viewport annotation options, go to legend and change from scientific to fixed one, apply. Okay. Now this is where the stress it has been changed up completely. Okay, so this is how actually it's deforming it. Like let me go for displacements also. Okay, this we can see that there is some error for applying this 0.572 and then we are stucking up with this particular error. Then what is this particular error and how to incorporate why this particular error is coming? All these particular details in detail, I just want to carry out this one. So to do that particular task, first go over here, click on monitor. So in the monitor tab that you can see this time increment required is less than the minimum specified. So when you just go to the paper that I have given you, here I have kept that particular paper. I just want to correlate with the paper and then I can tell you those things. So it would be quite easy for you also. Yeah, interrupting this warning messages and all. So when you just go for this particular things, so what's your warning message? So here the warning message that states that the time increment required is less than the minimum specified. So you can just go here, any kind of an error, like you just put it as time increment. So not this one. Node conversations that the time increment will be unattempted again, the time increment of an x. Okay. So system has a negative eigenvalue, the deformable, numerical singularities, the solution appears to be a diverging warnings. Okay. So I didn't see that particular things in this. So I didn't see that particular any kind of an error in this. So now the next back is like roll back over here and just go to the warning messages. We have seen about the warning messages. There are negative eigenvalues that it is creating of this. There are negative eigenvalues that's creating it this. The system matrix has a 1 negative eigenvalues. The system matrix has 11 negative eigenvalues. So there are a negative eigenvalues it is coming up this. Adjusted nodes were very small and not specified. There is for a type pair of, there is something under. I'm getting some disturbance from you. Can you mute? Yeah, thank you. So this is a compressive failure values must be a negative input has been taken of this. So this kind of an error messages that is coming. The system matrix has a negative value. So system matrix has a negative n values. Now you can see this. The system matrix has n negative eigenvalues. That is what the warning messages that we have seen. The system values has 59 negative eigenvalues. That's what we have seen. Now, what's the reason of coming this particular negative eigenvalues? Negative eigenvalues indicates that the stiffness matrix is not in a positive definite. For a procedures other than the eigen buckling, this is usually corresponds to the presence of an instabilities in the solution. So the load may have exceeded a linear buckling load. That means you were saying that the problem is with your load that which it may have an exceeded. For an example, negative eigenvalues can also occur when the second order elements are used to define your contact surfaces. Okay, so these two that we have to keep it in your mind. These two that we have to keep it in your mind. Negative eigenvalues do not necessarily indicate a problem with the solution. They may inherent to the problems. So from this, it was saying that the load may have exceeded the linear buckling load. The load may have exceeded a linear buckling load. That's what they were saying. Okay. Now, let me go on. And if you want, like, go to this message file. This is what nothing but like an Outlook file item that we can see in a folder. So when you just want, like, you can just go to the folders. That way we are solving this particular problems. I'm sorry. Yeah. Outlook item. So when I just go to this particular Outlook items, then here you can able to see all your warning messages, all your things that everything can be displayed, that whatever the warnings. So the system matrix has one negative eigenvalues. Okay, so the system matrix has a 6 eigen negative values and all. These are the warning messages you have normally. All are like the system matrix has a so and so negative eigenvalues, so and so negative eigenvalues. System matrix has so and so negative eigenvalues. Everywhere that you have seen a common warning messages, system matrix has a 59 negative eigenvalues and all. Note the solution appears to be a divergent convergent. So everywhere that wherever I check, the system matrix is having a negative eigenvalues and all negative eigenvalues. Having a negative eigenvalues and a very bigger number is a quite problem to the solution. But here with a limited thing, it's good. And again, solve our problem numerical singularity when processing the node number. So now you can just go here. Now you have this is called as a numerical singularity, right? You can just copy this one. You can you can just go here and check for this also numerical singularity errors and all. So now you have this solve a problem numerical singularity when processing the node and n degrees of freedom of the ratio. That's where the similar error that you can see it here. Similar warning. Processing a node at part so 1 of 1 and 945 is the node number. Degrees of freedom of a ratio 1 is quite challenging. So what this particular warning message says is that numerical singularities indicates that the so many digits are lost during the pass through a solver and the results are unreliable. Round of error dominates. So most commonly this is caused by an unconstrained rigid body. That means you are over constraining the model or you are unconstrained the model mode in a static analysis. So this occurs when there are insufficient constraints or it is a over constraints, like the boundary conditions are contacted to fix a body in a shape. And numerical singularities may also cause when an extreme stiffness difference is present. Stiffness difference is present. That means you see when there is an extreme stiffness difference is present, because in that means it is talking about our material properties. It is talking about our material properties. When an extreme stiffness difference is present, such as a very stiff spring connected to a very soft material, that means a very stiff steel connected to a very soft carbon fiber or vice versa. So numerical singularity warning should be ignored. They usually indicate the problem with the model definitions, while the situations may be obtained, it may be reliable. So take a note of a node of degrees of freedom. This is what I'm telling you this. This is why I have shared you this particular PDF. Hope you have this particular PDF with you, right, guys?
Yes, sir, I have.
Okay, so you have to go for this particular PDF whenever you just encounter any kind of an errors over here. So you just look up this particular warning messages in that particular file, identify that particular warning messages, and then you just try to paste them. So this is two errors. So one error from the negative eigenvalues, it's clear that maybe my loading condition I have to change. That's what I understood that. And the second error from the solver numerical singularity problems and all, I understood like maybe my boundary conditions are wrong. Maybe my boundary conditions are wrong, or the combination of the materials I have selected is wrong itself. These are the two possibilities from this particular warning message. Apart from this, any other warning messages that you have seen that you have to go and keep searching on this particular things at an each and every point that you have to keep searching for this. So we have only these two. We have only these two. One is a singularity error, and the one is a negative eigenvalues. Okay, let's say first we try to solve one particular step. Maybe my assumption of selecting the materials is maybe a wrong or something. So I don't know all those particular parts, right? So let me go over here and try to go to my loading conditions over here. Instead of loading conditions, I will switch off this one. So whenever you just want, you can activate it, or you want to deactivate it, you just click over here, it will get deactivated. I can just go to displacement, then I try to apply a displacement. That means the boundary condition procedure, I'm just changing it. Just try to apply this in a Z direction, maybe in a compressive 1 mm that I would like to bend. Maybe in a compressive 1 I would like to bend. I'm just arresting in all degrees of freedom. Let's it's free, or like you can just leave it all these things also. Just give okay. Okay, so now try to solve this. See, after seeing this particular material, they were clearly saying that a soft material is connected to a high stiffness difference. It is coming. High stiffness difference. It is coming. That means when they were talking about the stiffness difference of a part, then you should straight away look into the material properties error. Still, just want to go for monitor here. Then you can see this. This is how actually it is trying to solve. Maybe initially it started with an unstable steps only, but then slowly it is trying to pull it up. This is where whenever you see an unstable step, in an attempt I'd made to eat the biryani at that particular point, but it got failed. It got failed, maybe because of any other reasons, any reasons or not. So now the problem after reaching to point one, actually it got failed at. So let me go and monitor the results of this. So now see, I have seen up the stresses. I've seen up the stresses. I've seen this. Like I'll just go here. I will switch off this and elements over this. I can see this kind of a behavior. Let me go uniform. I can just make it as 10 times of it. Oh, maybe you can see a worse things. You can just get like something 5 times of it. So you can see this. This is how actually it is behaving. This is how actually it is behaving it. All the elements have got stiff and connected to this. So normally we need to give a lot of plasticity conditions also in this, but it is not there. So that's why you can see like this. Okay, so you can see this kind of a behavior, but it got again. We are seeing results, everything is coming, but still the solution is not completed, and it has been completed up to like so now just go to monitor over here, and then the same thing that you got it, time increment required is less than the minimum specified. When I just go to the matrix, so they were saying that all the warning messages that you have seen, it is like the system matrix has 236 negative eigenvalues. The other thing is like the strain increment is so large that a program will not attempt the plasticity calculations at so and so points and all. Remember this one? I'll come back. Apart from this, I don't have. So the other problem that the connection between these two, like singularity error warning messages, that it is gone now. Now we have the other thing is like strain increment is so large. So now you can just go, you can just put it as strain increment. So now see this one, that particular warning message that is there. The strain increment has exceeded 50 times the strain to cause the first yield at a endpoint. So the same thing that you have seen here, the strain increment is so large, or the strain increment has an exceeded 50 times in the strain to cause an yield at the 4 points. So that's what the error that I just need to identify it. So this particular problem states that it's a purely problem with your material properties. So you have to feed a more precise material properties it is asking. These normally occurs when the points in the model reach to your perfect plasticity. So now it has been reached to your perfect plasticity conditions. Maybe in our civil scenarios, we may never come across this particular warning message at all, because we always design with large factor of safety, right? So beyond the last stress of a plastic strain point, define the plastic cards, ABAQUS will assume the perfect plasticity. So the stress will remain constant while the stiffness drops to your zero. Stiffness will drop to your zero, but the stress remains a constant. In that particular cases, you can able to see this one. Check the material definitions and the plot contours of stresses and plastic strain and identify this one. So when you just want to go here, this was the results that I'm just seeing it, right? This was the results I'm just seeing it. Now you can just go to PEQ values and all. Now we can see this one. This is the maximum strain values that we have seen on this steel bar. Okay. Now from this, I understood it's reaching into your more perfect plasticity, whether I need to give more things. So the best way from here, it is like, again, adjusting my load point of view, my displacements point of view. Now I'm just trying to modify this particular displacement because it's still like lesser values, because it's going into your like more complete plasticity conditions, right? So I'll just going with like 0.1 as my things. Now this will solve 100%. So whenever you see any kind of errors, forget about the errors, dive into the Outlook file and then see what is the warning message that is coming. Go back and search what kind of a warning messages that you have inside the PDF file. Read that, correlate those particular statements with your model, and understand that where you are doing a mistake and try to figure out and overcome back that. Just going monitor over here. Now you can see this one. The problem is going smooth after reducing all this particular amount of loads and all.
Yes, sir.
So now it has been completed successfully for till the one step, it has been completed successfully. So that means now going up to the warning messages, again, I have a system negative eigenvalues itself. System again, I have only a system negative eigenvalue conditions and all that. So when you have this particular system negative eigenvalues, it's saying that it does not being a problem, but you have to make sure that you have to be like a more precise on this. Like you can just go with, system matrix has the negative eigenvalues. It's saying that the negative eigenvalues indicates the stiffness matrix is not in positive definite for our procedures other than the eigenvalue buckling. This usually correspond to the presence of an instabilities in the solutions. The solution is not in stable conditions. The load may have exceeded a linear buckling load, for an example. Now, still after facing this particular error also, when this particular eigenvalues are coming up, then you have to correlate this particular statement with your solutions and saying that like, yes, boss, I have an instabilities in my solutions because this is a carbon fiber material that which fails it very easily. And this is a steel component that which may not fail very so quickly. And I'm trying to distribute an equal amount of a load on the carbon fiber and as well as on the steel also, whereas steel doesn't won't bend that much of easily, but the carbon fiber will try to bend very quickly. But these steel component and the carbon fiber are tied up within each other, so that when this is trying to bend very quickly and this is not trying to bend so quickly, so there is a mismatch between these two. That's where it is causing an instability in my solution. That's what the statement that you need to give for that particular warning message.
Okay, sir.
You understood, right? These two are like connected
Yes,
within
sir.
each other, but this is not bending. This is going bending very quickly because of it's a carbon fiber. So now
Yes,
that's
sir.
where I have seen this. So in your system, so when a people come and ask you like, why you have seen a negative eigenvalues in your solution, can you give me a judgment? They were saying this here also. See this one? Negative eigenvalues do not necessarily indicate a problem with the solution. That means you have to understand why it is coming. If that why it is coming is at okay with you, then you can proceed with the solutions. If it is not okay with you, then you have to figure out a solution.
Yes, sir.
Okay, like this, you have to go and use this particular PDF to overcome the challenges that you are facing in your problems.
Yes, sir.
Okay, any doubts still now?
No, sir, not yet.
Okay, so now you can able to practice it, right? So
Yes, sir. Yes, sir.
if you are trying to model this particular thing as a solid, you can go it as like a engineering constraints and then give the material orientation and you can proceed it. Or else like if you want to model this as a lamina, then go it as a shell elements and then you can proceed for this. If you
Yes,
want
sir.
to go as a shell element, then you can go here and just apply a path, 3D, deformable, shell,
Sure.
planar, and then you can just go over here.
Yes, sir.
So you can just go, it is like this. Like again, that if you want, like you can able to extrude that into another directions also, and then you can able to make that as a shell, and then you can able to assign those material properties to this.
Yes, sir.
So you try working on this. If you have any queries, post me in the groups and try to get some errors and try to work out on this errors, understand this particular complete PDF. So once if you
Yes, sir.
understand this complete PDF, then you can become an expert in controlling of your problems as per the convergence issues.
Sure, sir.
Yeah. Okay then. If you have any issues, we can discuss. Otherwise, we can wind up the session.
No, sir. Currently, no issue.
Okay, fine. So to try practicing with these particular dummy values on your model and then let me know.
Sure, sir.
Okay.
Thank,
Take care.
thank you, sir.
Bye bye.